On Bluetooth.
Oh.
Yes, I know. So I started working heavily on Bluetooth starting in 2005, and I worked on it until Qualcomm bought my company and laid me off the week I turned 65, which was a little over five and a half years ago. So some of my knowledge is very detailed, but is becoming a little bit obsolete. Fortunately, they design all Bluetooth versions to be backwards compatible with all the new stuff. So what I'm telling you is relevant. It's just not complete any longer. So I want to talk about an overview of what Bluetooth is about, what problem they were trying to solve. You know, people don't invent stuff in a vacuum. Usually it's provoked by some market need. And talk about the general solution of a short range unlicensed radio. Talk about the evolution of the physical layer. How many of you are familiar with the Open Systems Interconnect 7-layer communications model? Any of you at all?
I know about it, but I don't have it memorized.
I was explaining it to my 425 class today, but that's another story for another day. Anyway, I'll talk about a little bit about the differences between classic Bluetooth and Bluetooth Low Energy, because they're similar, but they work slightly differently. I want to talk a little bit about applications, predictions, and resources. So what's the problem to solve? Okay, so mobile phones are starting to get common, well, starting to be introduced in the late 80s, early 1990s. That's when they had what they now call first generation phones. And the first generation phones, they were around, the bandwidth allocated to them was bits and pieces around 850 megahertz and 1900 megahertz. Each channel, for each subscriber, for any given connection, they give you a pair of 30 kilohertz FM audio channels. So it's an analog system. These phones are physically small, you know, fist size, maybe a little bigger. And they didn't have a lot of room for physical connections. You know, they had always a charging port because you'd put rechargeable batteries in them. They'd suck down non-rechargeable battery too quickly. Those of you who haven't been paying attention know that batteries are the most expensive form of energy, much more expensive than gasoline. And some of them had 3.5 millimeter headphone jacks if you wanted to put, you know, something on your head, right? So that was what we wanted to do. And the crucial resources are two. And one of them is time. End users, they need audio access to the call so they can talk and listen. And their attention matters. It's dangerous to drive distracted, as some of you probably know by now. In fact, the insurance companies and the state governments have been telling us for years now that distracted driving causes many more accidents than drunk driving does. So the killer application is wireless access to the audio, hands-free. Now, before they started putting Bluetooth in cars, we made up these little things, these little headsets that I'm going to model it for a moment. So I can talk and listen, and there's extra microphones on here so it can do some very crude noise canceling. All right, so those are the things that make this an important application, and that drove the success of the rest of Bluetooth. So let's talk about physical layers, how it delivers bits. Okay, so the essential is hands-free access to audio. And of course, this was driven by laws in many countries and US states. The people who drove it were Nordic-based Nokia and Ericsson. Nokia is based in Finland, Ericsson is based in southern Sweden. And those two companies were the main technical impetus behind it. A bunch of companies collected around them to make it a success, but it was driven here. The name Bluetooth was the nickname of a Danish king who united Norway, Sweden, and Denmark 1,000 years ago. And he had a dead tooth, so it had turned blue or black. And he got that nickname from that tooth of his. Anyway, this Bluetooth was invented to solve these connectivity problems in the late 1990s. I was at Microsoft at the time. One of my colleagues became their second general manager. So, unlicensed wireless spectrum. Why do we care about this? Well, most of the electromagnetic spectrum has restricted or licensed access. In the US, the Federal Communications Commission rules on all these things. Around the world, there's the International Telecommunications Union, and that's a branch of the United Nations. Now, some frequencies have a physical phenomena that makes them unattractive to the license. So if you were to look at a map of the spectrum today, you'll find a lot of spectrum before 2400 licensed, and a lot of spectrum above 2500 megahertz licensed. But that little piece from 2400 to 2499 is relatively unattractive. It's called the Industry, Scientific, and Medical Band, one of several. And the reason it's unattractive is that water strongly absorbs around that frequency. So if you're trying to send messages anywhere and there's high humidity, you're blocked. Now, the flip side of that is that's what microwave ovens use. I assume that all of you by now have zapped your food in a microwave oven, correct? Right? You all understand that, right? That's because that frequency is strongly absorbed by water molecules. It grabs hold of the oxygen hydrogen bonds and shakes the crap out of it, makes things hot. So that's why nobody wants to license that spectrum. They say, sure, you can have it because we don't want it because it's right. So now that area is quite crowded. So common to all Bluetooth radios is the ISM band. The wavelength is about 12 centimeters. The transmit power, the max is 100 milliwatts, but normally it's a lot less. Most commonly, it's 2.5 to 4, 2.5 milliwatts, which is 4 dBm. 100 milliwatts is 20 dBm. That's decibels with respect to a milliwatt. Does that make sense? So minimum power is a single milliwatt, which would be 0 dBm. The modulation is quite simple. It's frequency shift key first, or quadrature phase shift key, more on later slides. Does anyone know in advance what frequency shift key means? In all communications, you have to deliver at least bits, if not sets of bits. And the way you can deliver a bit is to deliver two phenomena which are distinguishable from each other. So if I've got a telegraph wire, the date's from 1837, the thing that's distinguishable is there's current or there's no current. In a legacy radio, you might have presence of carrier or no carrier. In frequency shift key, you have one frequency, which means a 0, let's say, and another frequency that means a 1. And you either send this frequency or this frequency. And the receiver can distinguish the two. And it calls them strings. Those turn into sets of ones and zeros. So GFSK means Gaussian frequency shift key. And so we'll talk more about that later. And we'll talk about adaptive frequency hopping later. But this is common to all Bluetooth radios. So we're using the ISM band. So we're using this set of frequencies. It's a digital radio. It's not sending analog. So unlike those first generation cell phones, we're not just FM modulating audio onto a carrier that has continuous changes in its frequency. We're sending one or the other. And 1 megabit per second was considered more than adequate for a digitized audio signal, which is our original target. So we'll talk more about that later. Two crucial innovations are frequency hopping and adaptive frequency hopping. Does anybody have any questions about those in advance before I dive into them? So classic Bluetooth, Bluetooth 1 and Bluetooth 2, they port 79 channels between 2402 megahertz and 2480 megahertz, 79 different channels, right? And each channel is 1 megahertz wide. So we're flipping between two frequencies that are close to their a center frequency, and their modulation index is between 0.28 and 0.35. So they're not changing, they're staying well within a guard band. If I were to a moment draw a picture, I'm going to find annotation. So I'm going to draw here, right? So at a given, here's the edge of a band, and here's the edge of a band. And so here is, imagine I'm drawing a frequency. Well, what we really do then is between let's call that 0.3. So let's suppose one frequency is up 30% and the other frequency is down 30%. So we'll send at one of these two frequencies. This is what it looks like in time. This is what it looks like in frequency. And then the receiver has to be able to demodulate and tell apart these two frequencies. Does that make sense so far? Anybody? Okay, so I'm going to clear that drawing and stop annotating. All right, so it was designed from scratch to survive a crowded and dynamic spectrum. The fact that nobody wanted to license it didn't mean it was easy. And what it meant is that everybody who wanted to do stuff around that frequency jumped into it. So the original versions of 802.11 for Wi-Fi use the same frequency bands. There's a lot of proprietary radios that occupy the same bands. There are cordless phones in the same bands. Has anyone ever heard of Zigbee before? IEEE 802.15.
Yeah, I've heard of that. I haven't used it. I've heard of it.
4, right. Zigbee is a different standard radio that uses the same band. So it's busy. So how do we assure good service to the end customers? So Bluetooth basic rate, that's what BR stands for, and extended data rate, which is Bluetooth 2, they each occupy 1 megahertz of channel bandwidth at any given instant, spread over 7980 channels. The master device and the subordinate device, when they pair, they exchange data, which is basically seeds their frequency hopper engine. So that each one, the transmitter and the receiver, will jump as a pair over these frequencies, and they jump at 800 hertz. So they're jumping pretty fast. And so the master device instructs the follower on how to do a tracking pseudo-random hop through those 79 channels. And in contrast, low energy has a higher modulation index, so it has a longer range, but each channel is twice as wide. So it hops over 40 channels instead of 79 channels, but otherwise it acts the same way. So let's see. I want to jump ahead first because this is a chart of what Bluetooth Low Energy does. So the channels are wider, but it works the same way. So all the blue lines represent hopping. So the transmitter and the receiver will say we're going to be at some place, and then they've got the same algorithm, so they'll jump to the next place, and then 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 the next place, and they'll hop all over the place. That's frequency hopping. And it means, amongst other things, that if there's something in the way, the transmitter and the receiver will either succeed in using the channel, and they'll remember that fact, or they'll not succeed in using a channel, and they'll remember that fact. So for adaptive frequency hopping, they will, if they have trouble with the channel, they'll avoid using it for half a second for 400 hops. They'll leave it alone. They might try it again after 400 hops to see if it's still working or not. And if it isn't working, they'll keep not using it. And if it starts working, they'll use it again. So that's a preview. Coming back to the range. So it was originally personal area networking. So we're talking about ranges basically within a room or a small number of rooms. Bluetooth since these radios transmit 20 dBm, 100 milliwatts, versus a small number of milliwatts, if we didn't frequency hop, it would be wiped out. So to get it to work, Bluetooth devices hop together. If it works, send and respond. If it doesn't work, log that fact and avoid that frequency for a while. I want to point out something else on this chart here. How many people here on this call have already studied 802.11? There might be none.
Like actually studied it or just kind of heard a little bit about it?
In the oldest versions of 802.11, it was only an ISM band. And it had a channel here, and it had a channel here, and it had a channel here. So when they designed low energy, people had looked at a lot of frequency plots over several decades, or at least the first decade, and they said, okay, if we're going to design a system that connects quicker, we're going to have 3 advertising channels, and those are deliberately chosen to avoid the most common 802.11 legacy channels. But what will happen in a real case, let's suppose you start using a Bluetooth headset, let's say, in your house, and you're sitting in front of a computer that's using ISM band to talk Wi-Fi as well. So that your computer will start using one of these bands, most likely. And what will happen is your Bluetooth devices will discover which of these bands is busy and then avoid it. And so they'll start using the bands that aren't busy. And if you happen to be in a house with two non-overlapping Wi-Fi bands, maybe one of them eats up this and one of them eats up this. And so the Bluetooth guys will jump around over here because they'll discover that they aren't blocked, whereas they'll discover that these are temporarily blocked. I'm trying to explain what adaptive frequency hopping means. So that's that. So they adapt and they'll hold off for half a second. So this is a summary slide of cores, Bluetooth cores. This one was from 1998, I think. And this one was from 2005, I think, Bluetooth 2. They had extended data rates. They basically doing frequency shift key here. And here they put out 4 phases or 8 phases at the same symbol rate so they could run 2 or 3 megabits per second. We had this adventure in 2009, where we decided, okay, let's use an alternate MAC and PHY, media access control and physical layer. So what if we could also use 802.11n? And we did this work so that suddenly you could work 100 megabits per second, but the market didn't seem to care. The market thought, well, if we've got a working Wi-Fi radio, let's leave the working Wi-Fi radio alone. So this spec is deprecated. So we had short range applications working. I'll explain later why we went to low energy, and then which is version 4, and then why we went to low energy 2 megabit and coded. Like I say, core 3 is deprecated. The market doesn't care. I will come back to this slide later a little bit. What drove the evolution? When Bluetooth 1 worked, people found more uses for it, which generate requests for more bandwidth. This happens everywhere. Every kind of system you can see, if people really, really like it, they'll come up with more uses of it and it'll get more popular and people will want it to go faster and lower power, et cetera, et cetera. That always happens. In your professional lifetimes, the same things will occur applying to things that I have no idea about yet. So Bluetooth 2, we went to a little bit faster rates. Bluetooth 3, we tried alternate MAC and PHYs. Market didn't care. The market generated needs for a low power. And we achieved this by radically reducing the duty cycle, including in Bluetooth 4 and 5. Now, how many of you, I've been teaching in my 425 class a little bit about power management. How many of you have ever heard about power management? You've had products that use it. You may not know it. All of you have smartphones. What do they do? Anyone?
Save energy if they can.
They turn themselves off as much as possible to get a lot of battery life out of their charge. So after so many minutes or seconds, they'll turn off their screen. And after some more time, they'll turn off more pieces of them. At minimum, your mobile phone, if it's just sitting there, it's part of a, let's say it's part of a an LTE network, 4G. So it looks like it's off and it'll wake up every 1.28 seconds and listen to the beacon coming from the local cell tower. And at minimum, it will spend a little bit of energy to say to that cell tower, I'm here. And that's all the system then needs to know. But if there's an incoming call for this number, the cell tower now knows where it is. So it will send messages saying, wake up, please. I've got a phone call for you. It might wake up. It might put up call coming in, messages. Why don't you answer the phone? That sort of thing. But it spends as much of its time off as possible. And this kind of work was being done after Bluetooth 1 was published. And so the market thought about it and came up with ways to contrast them. I'll get to that shortly. So here we are. Regular classic Bluetooth has 79 channels. And when one device is trying to find another one, they put up 32 basically inquiry channels here. And how many of you have ever lost or been lost by somebody at an amusement park? Has anyone ever been lost before?
Yes.
And how do you decide whether you're going to hold still so you can be found, or you're going to go looking for the other people? That's a tough question to ask. In Bluetooth 1 and 2, one device and the other device both put out rotating inquiry channels and listen for those inquiry channels until they cross each other, until one of them says, hey, are you out there? And the other one says, yes. And they form a connection, and then they bond and connect and exchange hopping patterns. And so they go into connection mode where they all hop together. That's how
So
regular Bluetooth works.
it sounds like when you're a kid and you get lost in the grocery store, you just start looking down the aisles.
Right, right. You understand.
That's
Intuitively, it's the same problem. So one of the things that we did when we had a chance to do a partial reinvention of Bluetooth, we said, okay, we're trying to optimize the system so it can be off as much as possible. That means one of the things we want to do is reduce the amount of time it spends finding the other devices. So in the redesign, we chose 3 channels for advertising. And so a device that wants attention will beacon and beacon and beacon. And that means a device that's listening for something to beacon only has to listen to 3 channels, not 32 channels. So the whole process can collapse down in time. So it connects a lot faster on average. So this, I'm going to come back to this because this is the 5.0 radio in detail. But here's the basic innovation for low energy. We want a low duty cycle achieved by low power achieved by reducing the duty cycle. So classic Bluetooth hands-free profile at, even though it's taking full duplex audio and compressing it to, let's say, 64 kilobits each direction, right? So that's 128 kilobits. And that's, you'd think that's only 1/8 of the 1 megabit bandwidth, but there's overhead involved too. So that actually becomes more like its duty cycle might actually, for 1 megabit, might be more like 30%. So it's burning power maybe 1/3 of the time. And if you run at higher data rates, maybe you can cut 30% down to 10%, but you're still kind of busy. Now, the counterexample, let's suppose we have a Bluetooth low energy sensor. And all it's going to do is broadcast some information once per second. And the way it works, which I'll explain in later slides, it might only take 3 milliseconds to advertise, connect, exchange some information, and hang up. which means 3 milliseconds out of 1,000 milliseconds is a 0.3% duty cycle. That means it's mostly off. So what we often observe is that the transmit RF power is somewhere between 1 and 10 milliwatts. And the power in the rest of the device might be comparable depending on how the sensor works. Now, in some cases like here, I've got my Fitbit smartwatch, and my Fitbit smartwatch is spending a lot of its time generating LED signals, trying to send light into my circulatory system, reading what comes out of my circulatory system, and gauging how fast my heart is beating. That's what this watch is doing. Now, it costs energy to run that LED. This thing figured out that I'd taken it off, and so it turned off the LEDs. But if I put it on again, it will start working again. And if I take it off, there it is. It thinks it was on again and it was working briefly. So the energy it takes to actually do your sensing might take more energy than an energy it takes to run the Bluetooth communications, in which case we've done our job. So let me show you about how this works and then go back to talk about Bluetooth 5. So imagine here's measurements in microseconds and things that are less than milliseconds. So it puts out advertising on a channel. And maybe it didn't get responded to. So it puts out an advertisement here, and this guy was listening and says, "Ha, I saw that. Scan request, scan response." They could go off and connect after that instead of continuing to advertise. Devices can advertise for a variety of reasons. They can advertise promiscuously. They can transmit signed data to a previously bonded device. Signed data means, first of all, it's authenticated, and second of all, it might be encrypted. They might advertise their presence to a device that wants to connect. Someone want to talk to me? They might reconnect asynchronously due to some local event. Tell you a true story. Docomo is to Japan what AT&T is to the United States. Biggest mobile phone provider, or they were at the time. And they have location-based services that they sell a lot to merchants and customers in Japan. The largest shopping center in the world is Shinjuku train station in Tokyo. And outside in the world, where they have access to GPS signals, so they have things that generate messages. Oh, you're near this store. They have a special on. Why don't you come on in here? Da 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 da. But down below, doesn't happen. So what Shinjuku did is they designed some little bitty Bluetooth low energy sensors that basically had a solar cell on them because they could run off of scavenged power. If they turn on the lights inside Shinjuku Station, there's enough energy flowing into these little sensors that keeps them lit. And the little sensors just sit there, and every second or so, they advertise, "Hey, I'm here." And if a phone hears them and connects, the sensor will say, "We are here. And these are the things that are going on in this store or in this restaurant or this whatever." So Docomo uses these little sensors to extend its network of location-based shopping services, because the energy can be so low that they'll run off of power. We'll get there. So if it finds a device and comes back, then the next thing is the master will say, here's something, the slave will see something, they'll ping back and forth until their transaction is done, whatever it takes. It can be very simple. If this slave, server has, let's say 16 or 32 bits of information to deliver, that fits very easily into a megabit per second message. In fact, most of the message is header, trailer, and CRC and routing information. It's not the payload at all. So it doesn't take very long to send these little messages back and forth. Once it's done, you're done. And both devices can go into deep sleep between transactions. So if I added up an example in microseconds, connection request takes 326 microseconds. And the radio is active a little bit longer. And an empty packet gets sent, not very long. Attribute protocol handle value indication. This is delivering the message. It can take basically a couple of milliseconds to deliver the data. Then you come back with an empty packet as an acknowledgement. And then you can send a terminate message. And this message says, yep, I'm acknowledging that we're done. Whole transaction, 3 milliseconds. And they're not even transmitting the whole time either. So here's the actual payload. This is the, shall we connect? Yes, let's connect. They can do all this stuff in not very much time. Let's suppose that they're in fact on for 3 milliseconds. And let's figure out what it would take. Let's assume it's 3 milliseconds total. That means the system is spending power for that much time. Let's suppose it's actually sending out 15 whole milliwatts, which is a lot. And I did these calculations back when we were building 40 nanometer chips. Now we're building, sub 10 nanometer chips. For a 1.5 volt battery, this is 10 mA. And if I take this many watts times that many seconds, I'm spending 45 microjoules per transaction. Let's suppose I buy a 180 milliampere hour battery. They're watch cell, basically. And here's an example of the device at that time in history, which was 5 years ago. They were about $2 in onesies. I could go into a store and buy them for $2. So if it's 180 milliampere hours divided by 10 milliamps spread out over time, I can do 64,800 seconds worth, which is over 21 million transactions. Now, if I spread them out over time, suppose the sensor sends a report every minute, not every second and not every hour. So I spend 1,440 transactions per day. So that means my duty cycle is quite small. Just for the BT low energy transactions, this is 15,000 days. If I divided this into this number, I get a battery life of over 40 years. Now, it's not going to run that long for two reasons. First reason is the batteries leak. The batteries won't be good that long. And the second thing is there'll typically be other processes running in the system besides the Bluetooth low energy stuff. For example, there's probably a little bitty microprocessor that is itself waking up, sleeping, and so on. There is energy being spent on the sensor, whatever it happens to be. There's probably energy spent on the local user interface, whatever that takes. Little tiny, let's see, little tiny displays, right? That takes some energy too. So maybe the total energy might be 4 times this, and it might only last 10 years, but 10 years is still a pretty long time for a battery. As I say, in fact, the communications cost will only be a part of it. The sensor could run on scavenged power like the Docomo example I picked up from ambient light. People are putting these in your shoes. People are putting them in car tires, and the ambient mechanical energy from the rotating car keeps them lit. And that's what powers those little sensors. In my car, if my tires get too low, they'll get a message from the tires that say, one of your tires is low, time to inflate it again. I get these things every couple months because I got a slow leak. So let's go back. This is what leads to low energy, and then go back to where we went. The latest version of Bluetooth, which is a few years old, basic low energy 1 megabit per second. This is the stuff I've been talking about. And it's Bluetooth 5 requires backwards compatibility with Bluetooth 4. Now we've got 3 new versions, keeping the same symbol rate, but using forward error correction. We basically double its range. Instead of being 20 meter inside a building and probably 100 meters outside of a building, it's now 40 meters inside a building and a couple of 100 meters out in open space. And that's an optional longer range. Here is, with more forward error control, we have 1/8 the data rate, but it's got 4 times the range. It could easily be 400 meters or more in open space. So that's so 2 versions of longer range are added in Bluetooth 5, and 1 version of higher data rate at 20% smaller range. That's when you basically double the symbol rate. You change frequencies twice as fast as in this case. And you always have a CRC to detect errors.
So if I recall right, Bluetooth 4 and let's see, what is it? You know how you can plug a USB 3 device into a USB 2 hub and it'll work. It just won't be the
Correct.
speed of USB 3.
Right.
So it's my impression. So correct me if I'm wrong. That it's not quite the same with Bluetooth.
Well, if you take a Bluetooth 5 radio and you connect to a Bluetooth 4 device, it will do this.
But what about a Bluetooth 3.2.1? Will it work?
Bluetooth 3, 2, and 1 do not do low energy.
Okay. So that's probably why.
So that's different. But every version of Bluetooth published since 2010, which is now 11 years, that'll work at least at this rate. At least at this rate here. Now, there is a difference. If you have a device that has older Bluetooth and newer Bluetooth, like my cell phone, like my iPads, like my Windows Surface 4 notebook, they'll all connect with Bluetooth Classic or with Bluetooth Low Energy, depending on what they're talking to. So they have wide connectivity. So I have here, for example, if I want to listen to music, turn this guy on, bond it to this guy, I can just sit here and listen to tunes. Works fine. Did I answer your question?
Kind of. I think it was about the basically the low energy mode.
Right. Low energy goes only back to Bluetooth 4, which
Okay.
is 11 years old.
So what I think I had tried to do is use a Bluetooth 4 device with a Bluetooth
Well,
3 phone.
there is no such, nobody makes a Bluetooth 3 phone.
I
Bluetooth 3
mean,
was deprecated.
oh, our
Bluetooth 1 or 2 is what you're talking about?
it must have been.
Okay. Yeah, the older phones, certainly phones made before 2010 didn't have low energy in them.
Right. Well, the phone may have been that old. This was a number of phones ago, so
Okay. Well,
it's been a while.
all right. So let me keep going.
Thank you.
So that's how do you get to low power? So let's talk about systems a little bit. The core specification, and you can go online and find it and download it, and it's huge. I forget how many pages it is now, but it's 5.1 is, several thousand pages. It defines the common physical and data link functions. The intermediate layers of the stack model data structures like packets and sets of packets. The upper layers define specifications for applications. They usually call them profiles. So here's an example of a Bluetooth stack. One of the things that Bluetooth does, which is relatively unique, is they specify all layers of the stack. They specify the core stuff, and they specify all the profiles as well. So I'm going to explain briefly what some of these things are. Physical layer we've talked about a lot. The data link layer is how you recognize where bits are and then make packets out of the bits. In the old days, people made Bluetooth controllers and a Bluetooth host was a separate device. You can still buy today a USB connected Bluetooth controller and stick it into your PC, and then the operating system, commonly Windows or maybe Mac, certainly Windows, will have device IDs for some USB connected Bluetooth hosts. And so you can hook into all of these things here and run these applications on your PC. Nobody makes a phone that doesn't have Bluetooth in it. This layer and this layer are part of the OSI layer 2 data link layer. Generic attribute profile and protocol collect data from the servers and wrap it to make it easy for it to be accessed and used by applications. And there are hundreds of these applications, some public and some proprietary. Some explanation. So the top layer is what faces the user. The bottom layer is how the bits are delivered. The link layer and the logical link controller, all called L2CAP, corresponds to the OSI data link layer. Identify bits, octets, and packets. These things model the data structures between an LE server and an LE client. This is logically what some of the things look like inside. This is obviously physical layer 1. These two here are the data link layers here. And then there can be synchronous unframed traffic or asynchronous and isochronous framed traffic. Audio, it tends to be isochronous. And if you're accessing data somewhere where the integrity matters, that will typically be bulk data. The intermediate layers for classic Bluetooth, Bluetooth 1 and 2, that's a synchronous system. They channel hop at 800 hertz. So at 1600 hertz, they're bopping back and forth. So the host sends a packet for 625 microseconds, which is the inverse of 1600 hertz. The host or device will then respond with a packet that's 1, 3, or 5 times that, depending on the nature of the traffic. Now, given a raw half duplex signaling rate of 1 megabit per second, the net full duplex signaling rate is around 300 kilobits per second. If you take out the back and forth part and the overhead part, that's how well it works. And it works well enough. Now, classic Bluetooth discovery is in one device broadcasts inquiry messages on 32 of 79 channels. The other device must be listening to those channels. So if you don't, push the button on both devices at the same time, one will be trying to talk and the other ain't listening, so nothing will happen. So pairing two devices is a user fraught problem. After each inquiry broadcast, senders listen for responses. Successful exchange of inquiry and response leads to connection. That's when they start hopping together. Now, classic Bluetooth topology is a master device can form an association of at least two devices in what they call a piconet. Now, you can have as many as 8 devices in a given piconet. There are some capstone students who are wrestling with trying to have more than 2 devices in a piconet so they can exchange data around a collection of people on Bluetooth. It can be done, but explaining that will far exceed the amount of time we have here. Now, given the range limitations of Bluetooth, a given device might be in range of 2 different piconets. And I'll illustrate it here. Imagine you've got a piconet, and here's a device that's in range of this, and a device in range of this. They may choose to adjust their timing. This device, being part of this piconet, might attach itself to this timing. If this device is common to both of these will probably have overlapping timing. And this device, also part of 2 nets, it may adjust the timing here to match this one. Here's a device that's too far away to be connected to anything, so it's all by itself. Does that help at all? I find I'm coming up on the hour time already. Shall I keep going?
I had a question
Sure.
about the figure. So device E in the middle over there, so it can decide either to go to the piconet around F or that piconet around A.
Yep. Actually, if it aligns its timing, it can participate in both piconets. Does that answer your question?
Yes.
But it'll be bouncing back and forth.
I see.
So Bluetooth low energy versus classic Bluetooth. Classic Bluetooth is synchronous, as I've been explaining, and LE is asynchronous at much lower duty cycles. Classic Bluetooth has 32 inquiry channels. Bluetooth LE has 3 advertising channels. Bluetooth LE has the generic attribute profile and attribute protocol to simplify how data structures are presented by servers to clients, and that makes the communication that they actually need to transact a lot simpler. It's not very verbose. What can we use it for? Well, let's see. In classic Bluetooth, basic rate and standard data rate, streaming audio is the biggie, and I use it all the time. And my phone is connected to my headset and to my speakers and to my car. So I can sit in my car, turn in my audio app on my phone, and jam cruising around town, And if somebody calls me, the car just flips over, the phone flips over to hands-free protocol so I can talk to whoever's calling me. And as soon as the call is over, it flips back to listening to tunes. Now, A2DP is the name of the profile that's used for one-directional stereo audio. A new application that's getting a lot of traction is wirelessly connected medical devices. So IEEE has a set of standards called 11073. I don't know where these numbers come from, but it defines data structures used for many, for several dozen different medical devices. And these, because you can't predict how busy they're going to be, BR EDR is used for these devices. There is also an adaptation layer because some of them can also run on Bluetooth Low Energy. But the first spec that's in wide use uses classic Bluetooth. What's Bluetooth Low Energy good for? Well, you can connect the things that we carry with us, like my watch, like tags. These are becoming a big deal. There are basically tracking devices that you can buy that use Bluetooth Low Energy that you can attach to things that you lose, like your phone or your wallet or your keys. And if you lose one of them, you can use your phone or some other device that's enabled with Bluetooth to figure out where they are. And that's a killer application in my family. Health and fitness sensors, this thing measures how far I walked every day. It measures my pulse rate every day. It's waterproof. It can tell when I'm swimming. They make blood pressure, pulse rate, blood glucose pulse oximeters that use low energy. We can use fobs to use, I lost something, where is it? Home and office automation for low data rate things. Sensors and controls in homes, offices, and factories. Low energy lends itself to things that run off of either scavenged power or needing to be recharged not very often. So you can install them and not pay attention to them for a while. And as I talked about, the tires and wheels can communicate to the rest of the car and tell you if the battery's getting flat or not. We can connect to anything that has intrinsic data to the internet. And there's a pretty big wearables market. It would take a long time to explain this all in detail, but take a look at the PDF. General sets of applications. Safety and security, I've lost something or I'm under attack. Sensing medical or fitness things, sports and fitness, lifestyle stuff. I attended a talk. I was the keynote speaker at the International Conference on Consumer Electronics in 2013. And one of the other speakers was the same lady who wrote this article. And her name is, let me find the article, I'll tell you, Mary. Come on. She works at Microsoft and she works on effective computing. And she was building sensors that measured aspects of like your sweat and chemical competition of your sweat and your pulse rate and your breathing rates and other things. And they were attempting to basically measure how you were feeling. Mary, Czerwinski, Czerwinski. She works at Microsoft. Anyway, she gave that talk on wearables 8 years ago, and I was pretty much blown away. I think that's really important stuff. Some of you might work in that space someday. So if you get IEEE Spectrum, find that article and read her article on effective computing. Obviously, we communicate with headsets and whatnot. And there are some people I've known who have wearables that are brightly colored and attractive in some way. I'm married to an artist, so she kind of gets it. I want to avoid explaining it here, but you got the basic idea. So I'm going to close up by talking about why Bluetooth has been successful, because there are many people proposing many different networking technologies that have fallen by the wayside. Bluetooth did not. I consider the three most important are legal policy. First of all, it had a killer app that had the law and insurance companies behind it. Like I say, the audio accident rate for distracted driving is worse than drunk drivers. So many countries and many US states enacted laws making driving and talking on a cell phone illegal with big penalties. So support for Bluetooth 1 and hands-free profile became the norm early in this century. So hands-free profile is a killer app. That drove success 20 years ago. Second of all, testing policy. So the Bluetooth Special Interest Group is a private organization with over 30,000 member companies, not individuals. And it has regular international testing events, plug fests. They've had 3 per year in some country in the world, going back to the late 90s. Builders of new devices are encouraged to attend those testing conferences and test their devices against other people's stuff. So if they run into problems, they're invited to informally share best practices with each other. Because Bluetooth is most successful if all their products just work. Do you follow what I'm saying? So Bluetooth has a very big incentive to make sure that everybody's stuff just works. So proof of interoperability is required to gain access to the Bluetooth compatible logos. And the flip side of it is every member of the Bluetooth SIG is required to pool any patents that they might have that apply to Bluetooth. And any device manufacturer who proves interoperability and pays the fixed license fees, and the license fees are in the order of 3 to 4 digits US dollars, right? They're not hundreds of thousands. They're much cheaper than paying lawyers. And you gain access to all these patents. So you're pretty much boring the lawyers, which is a popular pastime for me. So like the USB Implementers Forum, this keeps many patent trolls away. In fact, my last Bluetooth patent was granted in 2015, early in the year, and now they expire in 20 years. So my last patent will expire in 2035. I will be 84 years old when that happens, assuming I live that long. So everything else I've done is expired. So these legal testing and patent policy are to me, the keys. So several billion Bluetooth devices, at least as many Bluetooth devices as people are sold every year. So we're talking, over 10 billion devices per year. Now, here's some predictions, websites, articles, books, contact, right? Bluetooth LE is, in my opinion, to smartphones what USB has been to personal computers. You take a device like this, it has room for maybe one connector, right? Maybe two. This one still has a 3.5 millimeter audio jack, but basically you don't have a lot of room for physical connectors. So it connects to lots of things wirelessly, and LE is performing that function for devices like this. This thing, for example, I happen to own a satellite phone, text-only satellite phone. And there's an application that runs on here that talks to it by Bluetooth Low Energy. That's all it needs to do. Bluetooth Low Energy has advantages for low power or scavenged power. And I think networking these devices enables another wave of applications for Internet of Things. Here is where to go find Bluetooth specifications, all the way up to 5.2, which is the latest core. I've written these articles here, and if you guys needed access to them, I could find a way to share them with you. I have shared them with my class people. I put it on Canvas, but I don't know how to give it to you. One of you should send, I think that there is a Gmail address for IEEE Bothell.
Yeah.
Right. Somebody should send that to me, and I could send you these things as PDFs. My warning is that IEEE owns the copyright contact. As author, I have permission to share the material, but you cannot post it and share it in turn. All right.
Okay.
These are books that I like. I particularly, this lady, Jenny Bray, was my first boss at CSR. I really like Nick Hung's work. Robin Hayden used to work for me. He wrote the book on low energy, and this is another book on low energy. That's me and machines I'm famous for working on, and my email addresses. Any more questions before I sign off for the night?
I actually had a question. Someone asked me about this. Like, I noticed that, like, for example, my phone has an option where I could do mobile hotspot.
Yes, that's a Wi-Fi thing, not a Bluetooth thing.
No, but like the other option is it has something called Bluetooth tethering.
Okay, yes.
And I noticed you didn't mention that in the PowerPoint, so I wanted to ask you, like,
Right.
what is
There is, in fact, I used to be in charge of the subcommittee in the Bluetooth technical working groups for Internet Working Group. And what it will do is provide a Bluetooth connection for streaming data to and from whatever attaches to that functionality. And so it will take basically the signal path that goes over the mobile network, 4G or 5G or whatever. And it will collect that data and turn around and export it to another device with Bluetooth instead of with Wi-Fi. The advantage is the Bluetooth stuff is probably much lower data rate, but it's probably also much lower power as well. And if the application that you're exchanging data with doesn't need to deliver a lot of data, Bluetooth might be more effective. Certainly if you want the whole system to last longer.
Mhm. So in our case, like it's just doing what it normally does. It's just be like less internet data sent through.
Well, it's a lower bandwidth than Wi-Fi,
Mhm.
but it's also lower energy than Wi-Fi. So if you're streaming if you're streaming video over it, you want to use Wi-Fi. But if
Yeah.
you're streaming little bits of data,
Mhm.
Maybe connecting to your house security system, that doesn't need to deliver very much data. You might as well run it on Bluetooth rather than Wi-Fi.
So is Bluetooth tethering use like Bluetooth 5.0, or is it the classic, or you don't?
It's I'd have to read the specs from the manufacturer, but I'm guessing that it can use low energy to find other devices, and depending on the data rates, it might cut back to Bluetooth EDR if it's trying to deliver, let's say, 3 megabits per second. By the way, that last patent that I was granted is about how to use Bluetooth as an introducer technology for other things. Have you ever heard of Wi-Fi Direct?
Sounds a bit familiar.
Okay, well, in Wi-Fi Direct, normally you have, your broadband network and your modem and your Wi-Fi router and all your Wi-Fi things in your house talk through the router. But suppose I wanted to go directly from, let's say, my phone to this printer directly. How do they connect to each other instead of going directly through the local router? And the patent application has to do with having Bluetooth Low Energy in both devices, because they can beacon at very low power, connect to each other and say, oh, this is the radio you got? Oh, that's the radio I've got. What's your application? My application matches. You want to print and I'm a printer. Connect, and then go direct, and then jump from Bluetooth to something that's more power but much faster to burst over the image to print and then shut it down again. And it could also be used for LTE direct. Suppose you've got two 4G mobile phones, and in principle, they can run at hundreds of megabits per second. And ordinarily, they don't talk to each other directly at all. They all talk to the cell tower.
Mhm.
But using this technology, they could discover each other, talk to each other directly, and then shut down when they don't need the speed any longer. And it's being used, I'm told. So the company that laid me off was happy with it. All
Which
right.
company bought it?
Well, I was working for a company called Cambridge Silicon Radio.
Mhm.
And at the time that I went to work for them in 2007, they were the largest manufacturer of Bluetooth parts on the planet. They made the chips inside this headset. But they were bought by Qualcomm in the summer of 2015. The Chinese, believe it or not, have an antitrust division, and it took most of a year for the antitrust division in China to give them permission to buy CSR, which was an English company. And having that was approved. And then Qualcomm said, well, we're going to lay off 15% of our staff. So they laid me off the week I turned 65. And I had been thinking, I wonder how long I'm going to keep working. Shall I work till I'm 65 or 66 or whatever? And the fact that they laid me off the week I turned 65 simplified matters correctly. It said, well, okay, out of the pool. And I was very lucky because the next month, my wife was diagnosed with late stage ovarian cancer.
Mm.
So I spent most of 2016 being a caregiver. She's still alive. And if they hadn't laid me off and given me a severance package, I would have had to resign to take care of my wife, because that's the way things are. And so I was kind of lucky that they chose that.
Nice.
Anyway,
Who's
let me- what?
My other question is, who's still in the building in Kirkland that says Bluetooth on it?
Oh, the Bluetooth SIG is. That's
Okay.
their headquarters. The worldwide headquarters of the Bluetooth SIG is that office.
Looks like a small place.
It isn't. It only has it doesn't even have 100 employees. The reason I was attractive to CSR, they're based in Cambridge, England. And so I telecommuted to them for 9 years.
Mhm.
But I spent most of my time either thinking about public engineering standards or flying off to meetings. And it was very handy to them that I was right there 10 miles away from the Bluetooth SIG headquarters. Any problem at all comes up with Bluetooth and my company, I can be right there. I could bicycle there in an hour.
Are they
It'd
nice
take me
enough
longer to
answer
walk.
questions?
Yeah.
Oh, so you could like go there and say, "Hey, I just have a question."
They don't have an answer desk. They wouldn't know what to do with you.
Oh, okay.
And what's worse is you don't work for a member company,
Uh-oh.
because if you were part of a member company, they would have set up ways to accommodate your technical questions.
Okay.
But if you don't work for a member company and you don't join as an individual and pay their licensing, pay their, do whatever you have to do to be a member company, then they don't quite know what to deal with you.
Oh. Well, I guess maybe.
On the other hand, they do hire people. Now, they tend to like people with some experience. And one of the reasons in fact, the main reason I teach at Bothell is I want to pass on what I know about how to be a successful engineer while I still remember something, right? I'm trying to train the people who I would have hired in a previous life,
Thank you.
but I don't have the money to hire you now. So, yeah. But if you like working in this space, I have two bits of advice. One of them is study the material on your own as best you can.
Mm-hmm.
And when you're looking for jobs, find one that uses that technology. Because if you do, you will have joined a member company and get experience using that technology so that when you have enough industrial experience or your silly company lays you off, you can apply for a job at the Bluetooth SIG because they hire people.
Now, you're talking about using the technology as in making chips.
Well, making products.
Okay, making products.
And you can buy devices that have these chips in them and build the software that uses them.
Mm-hmm.
You ever heard of an ESP32?
Oh yeah, I have a number of them.
Right. And they have built-in Wi-Fi and Bluetooth.
Yep, it's great.
And so it's exposed to you as a programmer, in C or Python or whatever it happens to be that works on those machines. And yeah, learn to use the technology and then maybe go work for a company that needs that knowledge. I encourage all of you, if you haven't found your first employment job yet, is to experiment with whatever lights you up and gain the experience that teaches you stuff that we don't have time to teach you at school and would make you inadvertently attractive to many interviewers. I've interviewed hundreds of people, hired dozens of people, and I'm always excited to find somebody who has the initiative to train themselves. Which is, of course, why you want to join the IEEE, because they're a big source of more information all the time. That's their livelihood. Right?
Nice.
So I'm telling you, I'm preaching to the converted, I think. Anything else I can do for you, gentlemen? So I need to send the PDF of this presentation and the PDF of some of those articles to you, and then you can put them wherever you put them.
Well, I mean, would it be all right if you posted in our Discord then? Or because from
wait a
your
second.
wording,
Let's try something. I don't see chat
Okay.
in front of me, so I can't post it in chat.
oh, there's still chat here. Yeah. Mhm.
So you said something about shareability. How does that
I'll
work again?
I
stop.
can give